share my screen with you. And we can talk about it. Okay, so 12.4. So the title is Implicit Differentiation, which is a long word, so it's taking me a long time to write. Okay, so implicit differentiation. So first of all, the word differentiation just means taking, it's the act of taking the derivative. So if anything ever says, can you differentiate this function? It just means take the derivative. I know I've probably said it just a couple of times, but not necessarily, you know, explicitly said, hey, this is what I mean when I say differentiate. But you guys, we've been taking the derivative, you know, all semester basically at this point. So what is so special or different about implicit differentiation? Well, it all stems from the way my functions are written. So I'm going to give you an example or two of the functions we've been looking at, which have been explicitly defined. So when a function is explicitly defined, it means that y is by itself, basically, or your output is by itself. So here's an example of an explicitly defined function. Y equals 3x squared plus 5. So this is explicitly defined because y is the output, and it says y as a function of x equals 3x squared plus 5. Notice there's no y's over here, it's just x's. So in function notation, when you have f of x equals something, those are always explicitly defined because I know f of x, while it can be replaced with y, it just means the output. So you guys, if you ever do want to put a function in function notation, it has to be explicitly defined. You can't have y's, you know, on the other side if you're going to define it in function notation. So anyway, basically y is by itself. Now, when we take the derivative of this, for example, let's see, I would write derivative of y, or y prime, equals, and then I would do some power rule and get 6x, and that's it. So you guys, what I want you to notice about this, and it's something that we kind of overlook or maybe take for granted, is that while we take the derivative of this side, we're also taking the derivative of this side. I went from y to writing it as the derivative of y, because y is a function of x. It's not just x. So I don't always know what the derivative of y is, so we just write it as the derivative of y. But notice, the act of taking the derivative from here to here is happening just like it's happening on this side. So you guys, today, we're not going to be using this prime notation. Instead of saying y prime like this, I'm going to use the fraction notation where we have dy over dx. We don't use it too often, but I'm going to rewrite. So you have y. You take the derivative of y, I call it this. Remember that dy over dx just literally means the derivative of y with respect to x. So the with respect to part just means the derivative of y, assuming that y is a function of x. X is the input. X is the value that's changing. A lot of different ways you can say the with respect to part. So I took the derivative of every term in the function. And I always do, but when it's explicitly defined, this side is so easy. Like I said, I just don't think about it. I don't think, oh, I am taking the derivative of y. It's more like of a notation concept in your head, you know? But you are taking the derivative of the y as well as whatever's on the other side. So you guys, let's take this to the side. If you have x, so let's just say you start with an x. And remember, when you take the derivative, it's with respect to x. So if I asked you to take the derivative of this, and you might say, oh, well, there's really a 1 there, right? So you take the derivative of x, or 1x, and you just get 1. But what if I want to take the derivative of y? So why am I getting this dy dx is the question. So I could say, well, that's 1y. You guys, I'm actually using the same derivative rules for x as I do for y. The derivative of 1y is actually just a 1. I use the power rule to get that, just like I do for x. But what do I do? What special rule do I have when I'm taking a derivative that's not just x? You know, I always say that, but it wasn't just x. What happens? I use some chain rule, guys. I have to tack on the derivative of what this is because it's not just x. So I say, okay, well, how can I write the derivative of y? And that's why we just write dy dx. So you guys notice going from y to dy dx, is actually chain rule. It's actually chain rule that's happening here, and I don't notice it. So let's look at maybe a more clear example. So what if I had this? What if I had x squared? I am in a class. I can't buy you an iPad game right now because I'm in class. Stop. So what if I had this, guys? So when I look at a problem like this, I know chain rule is happening, right? Because I have x squared plus 3 to the 5th. What do I do? Remember, in my head, I say, okay, well, what if this was just an x? If it was just x to the 5th, what would I do? Well, and I do the power rule around the term, and I'm here, but I don't stop there, do I? I use the chain rule now, and I say, but this wasn't just x. So now I have to multiply by the derivative of what that was, and in that case, it's just a 2x. You guys, it's not as clear to see, but if I had, not a 5, sorry, but if this was y to the 5th, again, it's just one variable there, so it's hard to see that this is chain rule, but I work through it in my head in the same exact way. So I say, okay, so what if this was x to the 5th? What would I do? Well, I would do the power rule around it. And then I say to myself, oh, but it's not an x. So I need to multiply by the derivative of what it is, the derivative of y, which I write as dy dx. So guys, what we're going to see today is we're going to see some times when y, notice this y was not by itself. It wasn't explicitly defined as a function of y. So when y is not by itself, we're going to see y raised to powers. We might see y with some coefficients on it. Maybe I have 5y to the 4th, to start with. How could I deal with this? Well, if this was 5x to the 4th, what would I do? Well, I would get 20, and then this would be a cubed. And then again, I'm going to say to myself, but this is a y. It's not an x, so I just tack on dy dx. So what's the difference between a term with x's and a term with y's in terms of the derivative, you guys? I take the derivative just like I would it was an x, and then I just add a dy dx on the end. So using these facts, this chain rule business, I am going to move to equations that are not explicitly defined, which means they're not solved for y. Y is not going to be by itself on one side. And I move to equations that are implicitly defined, which just means it's not solved for x, it's not solved for y, it could just be a bunch of x's and y's anywhere in the problem. It's still going to be a function of x. For example, let's look at a line equation. You know how sometimes a line equation is written in what we call standard form, where you have the x and y on the same side? I know this is a function because I know it's a line, right? If I were to graph this relationship between x and y, it would be a function. It's just I didn't write it as a function or in function notation. I wrote it in this form where I have x and y's together. Well, instead of solving for y and getting y by itself, which I could do pretty easily on this one, I'm going to leave it implicitly defined, and I'm going to go ahead and take the derivative even though y is not by itself. So, you guys, when we differentiate implicitly, so when you have x's and y's on the same side, y is not alone, what you're going to do is you are still just going to take the derivative of each term separately. So let's start there. You guys, what's the derivative of 3x? Well, that's 3. Our rules aren't changing. So what would the derivative of 4y be? Remember, if it was 4x, it would just be a 4. But it wasn't just an x, it was a y. So I tack on with the chain rule the derivative of y, which I call dy dx. Here, the derivative of 10 it's a constant, so it's just 0. So we're here, guys. And notice I have a dy dx in my problem now. But you guys, I always have a dy dx in my answer. It's just usually it's by itself. So like in this first one, when I said y equals this, I took the derivative and I got dy dx equals 6x, okay? You guys, your goal from here is to get dy dx by itself. Whether you're explicit or implicitly defined, your goal is always to solve for dy dx. So it's not solved for now, but I can solve for it. You guys treat this as just a variable. We're not going to ever break it apart, not yet at least. So just treat it like any other variable, keep it together, and isolate it on one side. So I'm going to subtract 3 from both sides, and I'm going to get 4 dy dx equals -3. Then I'm going to divide both sides by 4 so I can isolate my dy dx, and I get dy dx equals -3/4. So I got my answer. Now, this one's a pretty easy one, and it's great for example. What if I had, instead of implicit here, what if I had changed it and solved for y? And then I could take the derivative explicitly. So how would I solve for y from this equation here? Well, the first thing I would do was subtract 3x on both sides, right? And then I would divide everything by 4. I would end up with y equals 10/4 minus 3/4 x. So you guys, if I had just solved for y in the beginning, it would have been easier for me just because it's the same thing I've been doing for a while. Well, what's the derivative here? So I have y. Let's go ahead and call it dy dx instead of using the y prime. This is a constant, so it goes away. Derivative of -3/4 x is still the same thing I got over here. So either way you do it, you get the same answers. It's just that what we're going to see today are some equations where, unlike this one, y would be very difficult to solve for. So maybe the algebra would be really tough, or maybe it's just impossible. Like, what if y is up in a power? While we could get it out, it might, be really complicated. So we're going to see equations where we're not going to solve for y like we did here. We're just going to leave it implicitly defined and take the derivative and then solve for dy dx. So let me show you our next example. So you guys, on this one I have x to the 5th plus y to the 4th equals 12. So again, I'm not going to solve for y. You guys, that would involve some fourth rooting, and I don't want to go there. I would rather just take the derivative of this equation as is. So that's what I'm going to do, you guys. So you take the derivative of each term. Derivative of x to the 5th is 5x to the 4th, and that is just an x, so that's it. Plus, you guys, if this was x to the 4th, I would just do power rule, right? So do power rule around it. and get 4y cubed. But because it's a y and not an x, I use the chain rule and I stick on my dy dx. Basically, whether you want to think about it as the chain rule or not, if that's a confusing concept still to you, every time you have a y term, you're going to get a dy dx in your answer. It's just, you can just think about it that way. Use that rule of thumb. And you guys on the other side here, the derivative of 12 is just 0. So remember from here, just like we did in the top, your first step is always to take the derivative of each term. Your second step is always going to be to solve for dy dx, which is one way to remind you that you do need a dy dx in your equation. So let's say you forget, you guys, you just say that it's 4y cubed and you forget that there's a dy dx on there. Well, think about your next step is solving for dy dx. If there's nothing here, how can you solve for it, right? So you have to have a dy dx somewhere in your equation so you can actually solve for it. So just isolating the dy dx, let's go ahead and subtract the 5x to the 4th from both sides. And then I'll get 4y cubed dy dx equals negative 5x to the 4th. Now to continue isolating dy dx, I can divide both sides by 4y cubed. And I end up getting dy dx by itself, and it equals negative 5x to the 4th over 4y cubed. And it's not the prettiest derivative I've ever seen. Sometimes these are going to look a little messy and complicated, and that's okay. It's because the equations they come from, if we were to solve for y, would have been pretty messy and complicated. Okay, so this is what I get on that one. Let's do another one. We're just going to do a lot, basically. We're going to do a lot of examples. I want to do 10x cubed minus 2y to the 5th equals negative 6. So this one's got some coefficients on it, not too different from the one we just did though. So derivative of 10x cubed is 30x squared. Derivative of minus 2y to the 5th is going to be negative 10y to the 4th, but because it was a y, I get that dy dx term on there. And then derivative of this is 0. So very much like the one we just did, I just need to solve for dy dx. So I'm going to subtract 30x squared from both sides and get negative 10y dy dx, or sorry, I left out a term, negative 10y to the 4th dy dx equals negative 30x squared. And then divide both sides by negative 10y to the 4th. And I'll end up with dy dx equals negative 30x squared over negative 10y to the 4th. But you guys, if you can reduce this fraction, then definitely reduce it. So I can do the negative 30 over 10, and that's just going to leave a positive 3 on the top if you take 10 out of both of those, or negative 10 out of both of those. And you'll get positive 3x squared over y to the 4th. So once you actually take the derivative, it's just algebra skills, basically, right? As long as you do take the derivative correctly and you remember to put in that dy dx. Let's throw a product rule in here because we can. Let's do x squared y to the 5th equals 19. So all the rules apply as they've applied the whole, the whole time that we've learned them. We just have that extra little thing to think about now that we have y's in the mix. So you guys, this has to be product rule. How do I know? Well, it's the product of two things that I can't actually multiply together. There's no way to combine these terms because they have different bases. So I have a product of these two things. Label one of them u, so u is going to be x squared, and v can be y to the fifth. Find the derivatives of each of those. So the derivative of u is 2x, and the derivative of v is 5y to the fourth dy dx, because that's a y. So notice here, just because this x term is attached to the y, when I separated them into two separate things, notice the u's don't have to worry about dy dx's because u only had x squared in it. The only time I had to worry about the dy dx was in the v term that had the y. So now I'm going to put it together with the product rule. So I have, this is going to equal u times the derivative of v. So that's 5y to the fourth dy dx plus v, which is y to the fifth, times the derivative of u, which is just 2x. And you guys, so I took the derivative of this side. Derivative of this side is just 0. So before we move on, notice this term here does have a y in it, and you might think, oh, there's a y in that term, so it needs a dy dx. It doesn't though, right? Because this was just original v. It didn't want a derivative on v there. It just wanted original v, and that was just y to the fifth. So this term isn't involving any derivatives of y, so don't just stick one in there because there's a y there. It's covered here. Okay, so let's clean up what we have a little bit. I'm going to call this 5x squared y to the fourth dy dx. I don't know why I keep putting equals here when I have one on the other side. Plus, let's call this 2xy to the fifth. It just looks nicer when the number's in front. It's really not a huge deal, but here we are. So you guys, I'm trying to solve for dy dx, so I can take this whole term away. Let's subtract on both sides. And what I'm going to be left with there is 5x squared y to the fourth dy dx equals negative 2x y to the fifth. You can divide by everything over here. You guys divide it by 5x squared y to the fourth. And what we end up with is dy dx by itself. And it equals all of this, you guys, negative 2x y to the fifth over 5x squared y to the fourth. But you guys, we can reduce a lot of things here. So I have y to the fifth over y to the fourth. If you take y to the fourth out of both of those terms, then it'll leave you with just a y on top. What about the x over x squared? Take an x out of both of those, it'll leave you with an x on the bottom. And then you still have the negative 2 over 5 because those don't reduce. But you guys, this is what your answer would need to look like. So any reduction you can do, definitely do. Sometimes you can, sometimes you can't. You always want to try at least. Make sure you have the most reduced answer you can. Let's do an e. Let's put one with an e in here. That's always fun. What if I have 5x squared equals 1 minus e to the x? I'm sorry, I said x. It's actually e to the y. That would be too easy. And we wouldn't have any y's in our problem, which would be a problem. Anyway, guys, so here we are. 5x squared equals 1 minus e to the y. Like all of these problems, I just need to find dy dx. So my first step, as always, is to take the derivative of each thing separately. So you guys, the derivative of 5x squared, that's just 10x, equals derivative of 1 is 0, minus, let's talk about the derivative of e to the y. Well, if this was e to the x, what's the derivative of that? Isn't it just e to the x? So even though it's not just an x, remember how chain rule works on exponentials. You actually bring the e term down exactly as is, right? So I did that. Then you just take whatever's in the power and multiply by that, the derivative of that. So that's where I get my dy dx. So again, these derivatives, guys, with the y's, you do them exactly the same as if they were an x. All that ever happens is you get a dy dx on the end every time. So here I have 10x equals negative e to the y dy dx. Remember, your only goal is to solve for dy dx. So I'm just going to divide both sides by negative e to the y. So I get 10x over negative e to the y equals dy dx. And that's it. So guys, again, if you had forgotten to tack this on, you wouldn't have had anything to solve for. And I think that's a really good, you'll notice as you go that that's a really good reminder to put that dy dx in there, because at some point you've got to solve for it. So it has to be present. Let's see, what do I want to do next? Ooh, let's do a natural log. That'd be fun. I want to do 3 natural log x equals 4 minus natural log y. Okay. So again, taking the derivative of each term. You guys, this 3 is just a coefficient on the natural log x, right? So the 3 comes down. How do I take the derivative of natural log x? Remember, it's just 1 over whatever's here, right? And this is just x, so it really is just 1 over x. Derivative of 4 is 0 minus, well, what do you think the derivative of natural log y is going to be? Remember, you have the natural log of something, you take the derivative, it becomes 1 over that thing. Remember, we're treating it just like it's an x. What do you think I'm going to add on because it's not just an x? I'm going to use the chain rule because you know that's how natural log works. If this isn't just an x, you tack on the derivative of what it is. So here I'm going to have 1 over y dy dx. So this term I'm going to call 3 over x equals negative 1 over y dy dx. To isolate the dy dx, let's divide both sides by negative 1 over y, which is really multiplying by negative y, right? Because I flip and multiply. So over here, I'm going to have dy dx by itself. And you guys, 3 over x multiplied by negative y just makes it negative 3y over x. So I know you want more examples, and that's just what I have for you. So let's do some more. Let's do 8y times the natural log of x equals 15. This is just practicing this stuff is what's going to make it comfortable for you. Okay, so 8y natural log x equals 15. Notice this is going to be a product rule. You can't actually multiply 8y times the natural log of x. They're two separate things multiplied together. Let's call one of them u, and let's call one of them v. Let's take the derivative of u. So the derivative of 8y is 8 dy dx. The derivative of v, so natural log x, that's just 1 over x. Let's put it together so I can get the derivative of this side. So it's going to be u dv plus v du equals 0, because the derivative of 15 is 0. And then just get to work on solving for dy dx. So you guys, this 8y times 1 over x, I'm going to go ahead and call that 8y over x. Plus, I'm going to put this 8 in front. Let's say plus 8 natural log x dy dx. So I haven't really done anything in that step, just wrote it different. Let's subtract 8y over x from both sides. And I'll get 8 times the natural log of x dy dx equals negative 8y over x. Let's now divide both sides by 8 natural log x. And what you're going to get is dy dx by itself here. And you guys, when you have a fraction and then you divide it by another thing, all that's going to happen is this thing's going to end up on the bottom with the x. So just, so you don't have to do a bunch of fraction, flipping and multiplying stuff. For example, if you have 1/3 and you divide that by 2, what do you get? You get 1/6, because what ends up happening is this value you're dividing by just joins the denominator. So that's what's happening here. You're going to end up with negative 8y over x times 8 natural log x. It just joins the denominator. Another thing to divide by. And then from here, you're just going to reduce your fraction as much as possible. So you guys, this negative 8 and the 8, you can cancel those and end up with just negative y over x ln x. So be careful here. While the 8 and the 8 do cancel, that negative stays. But this is your final answer there. Let me see. I think I just want to do one more. I want to do one that has the product rule with an e term. So let's do x cubed e to the y equals 13. Okay, so if this is what I have, and I want to take the derivative and then solve for dy dx, I have to use the product rule again, because it's two functions of, well, even y is a function of x, remember, so it's two functions of x multiplied together. So your first term, u, can be the x cubed. Your v can be e to the y. So du here is going to be 3x squared. But dv, I know how to do this because I did it before. The e term comes straight down, then I multiply by dy dx. All right, so I'm here. Let's put it together. X cubed times e to the y dy dx, that's u dv, plus v, which is e to the y, times du, which is 3x squared, equals 0. And again, here we are, ready to isolate dy dx. So let's subtract this term from both sides. What that is going to leave us with is x cubed e to the y dy dx equals 3x squared e to the y, or negative 3x squared e to the y, because we had to subtract. What am I going to do next? Divide both sides by x cubed e to the y. Remember, I'm trying to isolate dy dx. And I get dy dx equals, let's just put it all together here, and then I can reduce. So on top, I have negative 3x squared e to the y. On the bottom, I have x cubed e to the y. And then I can reduce. So you can cancel out the e to the y's totally, you guys. So those are just gone. With the x's, if you divide x squared out of both of them, then there's none up there. And then this just becomes x. So you just end up with negative 3 over x. So all that work with the product rule and all of that, my derivative actually ended up being pretty simple. But there we are. So you guys, after my classes are over today, I'll be putting up a part 1 of this 12.4 homework. On Wednesday, we'll look at part 2. But I would suggest looking at this part 1, and practicing some problems before we start the next part, just so you're super comfortable with the process. You might see some practice problems that, honestly, most of them aren't going to have derivatives that are any more difficult than the ones we've looked at. I might throw some different things in there that I worry about it, but I think it's all going to be pretty clear. One thing I want to do is, you guys, what if you had, and I don't know if it's going to come up or not, but we did e to the y a lot. What if I had like e to the y squared? You know, or something like this where it's more than just y here. Well, just remember how you would treat it if it was e to the x squared. And then, you know, you're just going to add on a dy dx at the end. So first of all, you would bring the e term down as is, because you always do. So you're going to bring down the e to the y squared. Then you're going to multiply by the derivative of y squared. So I know the derivative of y is just dy dx. But what's the derivative of y squared? Well, isn't that just 2y dy dx? So you're still going to get your dy dx in there. There's just going to be more to this derivative than just that. So on this one, it would look like that. So this would just be a little more involved when you take the derivative, but you still have the dy dx in there. If you had e to the 3y, well, you would bring it down as is, e to the 3y, and multiply by the derivative of 3y, which, you guys, if you have 3y, derivative of that is 3 dy dx. So notice you're adding on more than just dy dx in some cases, and in those cases you would have more than just y in that power. Like I said, I'm not sure if you come up with that or not, just in case you do. Remember, you still treat it the same way using the same method. It's just that you might be tacking on more than just dy dx. Okay, but yeah, so look for that later this afternoon. Look for that part 1 homework. Try to work on it if you have time before we do part 2 on Wednesday.